Okay, lecture 39, gravimetric analysis and volumetric analysis. And you should know those definitions. Now I started this and kind of interrupted myself so many times I thought I should start again. These gravimetric analysis problems involve a precipitate, and that precipitate contains the thing that we're after. In this case, the precipitate is silver bromide. We're after the bromide. Well, the bromide is part of an unknown ionic compound. We dissolve it in water and we get the bromide ion in solution. We add silver nitrate, so we get the silver ion in solution, and those react together to form a precipitate. We weigh the precipitate, and from that we can get the mass of the bromine. That's what we're going to do. So that's what happens. You have something in solution, or you put it into solution, add a counter ion, it precipitates out as a solid, weigh the solid, and then backtrack to your mass. So there's a lot going on here. That's why this is such a large looking problem, but it's very straightforward. So we have this 0.866 grams of the unknown ionic compound that contains bromine. We treat it with the silver nitrate, which produces silver bromide as a precipitate, and that weighs 1.54 grams. And then they want to know the mass of the bromine and mass percentage. Well, we don't know the mass of the bromine. We do know the mass of the silver bromide. And from there, we're going to find how much of the bromine. So this is really a mass percentage problem here. We're just going to go from grams of silver bromide to grams of bromine first here. So we have silver is 108 plus the bromine, which is 80. So this is 188 grams of silver bromide is 1 mole of silver bromide. And for every mole of silver bromide, there is 1 mole of the bromine ion. And 1 mole of bromine ion, even though there's an extra electron, it's essentially the same mass. If you can tack on the mass of 1 extra electron, you'll find that it, by rounding, it disappears. So 1.54 divided by 188, that gives us the moles of bromine, and 1 mole of moles of silver bromide, and 1 mole of silver bromide is 1 mole of bromine, so the same value, times 80, that gives us 0.655 grams of bromine ion. So that's the first answer, and the mass of the bromine is 0.655 grams. So in the original sample, that's how much was present in bromine, and then the mass percentage is just the mass of the bromine divided by the total mass of the unknown times 100%. So 0.655 divided by 0.866, and we come up with 75.6% by mass. So 75.6% by mass of that sample was bromine. All right, let's take a look at another problem here. We'll just do one more gravimetric analysis problem. The concentration of lead ions, cadmium, in a cadmium ions. I'm not redoing this. Cadmium ions, Cd plus 2 in a sample of water is determined by adding solid sodium sulfite to 200 mils of the water sample. 0.337 grams of cadmium sulfite precipitated out. Calculate the mass of the cadmium. So it should have been cadmium. I don't know, I had lead in there. But what happens is we have the cadmium ion plus the sulfite ion react to form cadmium sulfite, which is falls out of solution. So we have the cadmium, should just be a C here. So we have the cadmium that's already in solution. It's just sitting there. We add in sodium sulfite, which is, make sure I have it up, Na2SO3. The sodium does nothing. The sulfite ion reacts with the cadmium, falls out of solution, and we have 0.337 grams of cadmium sulfite. So we see, again, a precipitate. What we're after is the cadmium. We have something else attached to it, so we have to get rid of that extra. So cadmium is 112. Sulfur is 32, 48. So this is 192. And I'm going to double check that right now. 48 plus 32 plus 112, 192. Okay. So 1 mole of the cadmium sulfite is 192 grams. 1 mole of cadmium sulfite contains 1 mole of cadmium plus 2, and then 1 mole of cadmium plus 2. Even though it's missing those 2 electrons, it weighs the same amount once we've rounded. And you can certainly check on that too. So take cadmium, the molar mass, and subtract off the mass of the electron. You're going to find that it's, in this case, inconsequential. So we have 0.337 divided by 192 times 112, and we end up with 0.197 grams of cadmium. And the mass of the, okay, so this is the mass of the cadmium, that's what we're after, and then the concentration of cadmium. Well, fortunately we had to find the mass first, so now we have to convert back to moles. That's what we would have had if we would have stopped there. But, you know, sometimes you have to backtrack, no big deal. So we found out our first answer. There was 0.197 grams of cadmium present in the 200 mils. And what are we doing here? Okay, so this is 1 mole. Okay, so 0.197 divided by 102, 0.00176 moles of cadmium. And we want the molarity, so we take the moles and we divide by our volume in liters. And our volume was 200 mils, so that's going to be 0.200 liters. Make sure you always get into the liters if you're going to find molarity. You've been off by a factor of 1,000, and this is our molarity. And I'm going to just double check everything before we go on. Yep, and then divide by 0.2. Yep, that's the deal. Now, so those are 2 gravimetric analysis problems. You can see we end up with a precipitate, weigh it out, and then convert those grams of precipitate to grams of whatever ion we're after. Lots of different possibilities. I did an anion one and a cation one, but that's pretty much the same way you do all of them. Okay, now we're into volumetric analysis. There's a lot more here because it deals with solutions and titrations. We do a lot of this in chemistry, in our labs, and in calculations in later chapters. So I want to cover a few of them here. A flask containing a solution of unknown amount of acetic acid is titrated with sodium hydroxide. Titrate means we're adding the sodium hydroxide, and so what we know from previous work with acids and bases, this is what should be the reaction. Should be able to find this. We've done this for finding the complete and net ionic equations before, so this is the molecular equation, but this is what we'd start with. It takes 5.78 mils of this solution to complete the reaction. What is the mass of acetic acid in the solution? Okay, so if we take the concentration of the sodium hydroxide, so this is moles per liter, we multiply it by liters, we end up with 0.15 times 0.00578. Make sure that extra 0 is in there. 8.67 times 10 to the minus 4 moles of sodium hydroxide. I said that extra 0, and I didn't put it in there, but I did when I did the calculation. Times 0.00578, I think it did. Yeah, okay. And because this is 5 mils, so it should be, you're going to move this, make sure I'm on the page, 1, 2, 3, so there'll be 2 zeros. That should be there. And I did the calculation. I'm going to just triple check it this time since I said one thing and wrote another. But, yeah, that's the guy. Okay, and then once we have the moles of the sodium hydroxide, we can then use the equation to determine how many moles of acetic acid reacted, and then convert to grams. So 1 mole of sodium hydroxide will react with 1 mole of acetic acid. So this is how all of these volumetric analysis problems will go. And then for every mole of acetic acid, that's 60 grams. And I'm going to double check that. That one is very familiar with, but just to make sure. So 32 plus 4 plus 24. Yep. And so what we have to do here, we're adding in a volume of a certain concentration of sodium hydroxide. If I had just given you the moles, if I had just given you this, then this is a chapter 3 problem. As I convert moles of sodium hydroxide to grams of acetic acid. We've done that one. So here's just an extra step. Take concentration times volume gives us moles. Then we can work with the equation. As a hint, I just wrote out the equation here. On the exam, generally, for these types of problems, I give you the equation. When you're given an equation, you know you're going to use it. So make sure that, and since it's an equation, or the coefficients are in moles, you're going to have to convert to moles, most likely. Very few times when you're given an equation that you don't have to convert to moles. So, so that gives you kind of a lead if you've forgotten how to do the problem. So, well, if it's an equation, I have to convert to moles first before anything else can happen, and maybe from there, if nothing else, that can jog the memory. So we have what is the mass of acetic acid? So, yep, we're done. So take the concentration times the volume gives you moles. Use the moles with the equation to determine the moles of whatever we're after, and then convert that to grams. Okay. Another problem, 20 mils sample of unknown monoprotic acid. This is an important one to do because a monoprotic acid is just one that will react 1-to-1 with sodium hydroxide in this case. There's only one H+. And in the next class, using HA as a general monoprotic acid, one that has only one hydrogen, becomes how we do things. So might as well bring it up now. 20 mils sample of unknown monoprotic acid is titrated with sodium hydroxide. It takes 45 mils of sodium hydroxide to complete the reaction. So we have sodium hydroxide. Remember we had acetic acid that was HC2H3O2, but this is just HA. A is the counter ion, and acetic acid is the acetate ion. Well, we're not going to worry about what it is, and that's why we often put it into this form, because just saying HA, that's all that's important, is that it's an acid and it only has one H+ to react. So this is going to be a 1-to-1 problem. So this is going to be aqueous, aqueous. So it's a little weird looking, but we could have put in, let me just show you what, we had HCN, that's monoprotic. Could have certainly put that in here. Same thing, the A is this CN, but it could also be, if we had HF, it could have been the F, but you see that everything would react, all of these monoprotic acids react the exact same way. So anyway, it's still 1-to-1, that's the important part. Now it says, what is the concentration of the original acid solution? Sometimes we don't know what the acid is, we just know that there's something in solution, but we can still find the concentration because we deal with moles. We don't know what the acid is, so we can't convert to grams, because we don't know its molar mass, but we certainly know it's how many moles we have, because what we do is we take 0.1 molar of the sodium hydroxide, multiply by its volume that we used during the reaction. It says 45 mils, or 0.045 liters. And that should move the decimal place over just 1. And so this is moles of sodium hydroxide. From the equation we see it's 1-to-1, so this is going to be equal to the same number of moles of HA. But I can do out the calculation. So, but you'll see that we have moles of sodium hydroxide. For every mole of sodium hydroxide, it's 1 mole of the unknown monoprotic acid, so it should be the same number of moles of HA. So we know how many moles of HA we have, and now to find the concentration, we just divide by our volume. Our original volume, not the volume after the reaction, which would be 65 mils. We go back to the original. That's what we started with before we added any sodium hydroxide, so this would be 0.02 liters. I bring this one up too because it's so important in the lab. You need to be doing, and we will do problems where we'll involve this, that will involve this type of calculation, and especially next the second semester. But if you stay in chemistry, you'll really be dealing with unknowns, but because we were dealing in moles, as long as we know the ratio from the equation, we're all set. Okay. Now, 5. How many milliliters of 0.175 molar sulfuric acid are required to react with 12 grams of potassium hydroxide? This one I bring up because now instead of being 1 to 1, it's going to be 2 to 1, or 1 to 2 here. This is our equation, and we get 2 moles of water. Because a lot of times in these types of problems, students fall back on the dilution equation, Mi times Vi equals Mf times Vf. That will work as long, I mean, if you don't know what I'm talking about, that's fine. It's actually better that you don't know. But if you've gotten into the habit of using that, here's one where that technique won't work. Because instead of, the only reason it works is because everything's 1 to 1. 1 sodium hydroxide to 1 HCl. Here, it's 1 to 2. So if you use that technique, if you know what I'm talking about and you use it without thinking, you're going to be off by a factor of 2. So it's better to do it out the proper way. That is, instead of using the dilution equation, use the tools we learned from the 3rd chapter. So here's how we do this. Well, how many mils of sulfuric acid are required? Well, first we need to figure out how many moles of potassium hydroxide we have, then use the equation to determine how many moles of sulfuric acid we need, and then we can use the molarity to determine the volume in liters and then convert to mils. And I do that a lot, where I tell you what we're about to do, and if it's just a jumbled mess, you don't understand it, just continue on. You can see that I'm going to do the problem out. But if you have any understanding of this, it's good to listen to my description and see if you can follow it through, follow the logic. What I'm telling you is definitely true, but don't let it throw you off if it's something you haven't thought of up until now. So plus 16 plus 1. So this is 56.1 grams of KOH is 1 mole. KOH, I'm going to double check that. 39.1 plus 16 plus 7. So, and now now that we know moles of KOH, we know that for every 2 moles of KOH, notice I don't use any decimals here because it's these are exact numbers taken direct from the equation. And that's as far as we have to go because we need moles of H2SO4. Here's where that 2 comes into place. That technique that I talked about earlier that some students know, what they're essentially doing is this calculation without that 2, and you can see that that's pretty important. It's going to change our value quite a bit. So we have 0.07 moles of H2SO4. And we need to know how many mils. So we know that we have 0.107 moles of H2SO4. And if we divide by the molarity, or invert it, as I'm going to do here. So instead of multiplying by the molarity, we're dividing by it. So it's going to be 1, and this is going to be 1 liter. So H2SO4. So let me just do a real quick double check here. 12 by 2, okay. So we have this many moles, we've determined that, and then we divide by the molarity, and we end up with 0.107. 0.611 liters, and they want it in mils, so that's going to be 611 mils. So what this says is that we're going to need 611 mils of 0.175 molar sulfuric acid to react with 12 grams of potassium hydroxide. And let's go through really quickly here. Well, if you're given grams of something and you're also given an equation, you're most likely going to have to convert that to moles if that species is found in the equation. So convert to moles. Then using the equation, for every 2 moles of KOH, we have 1 mole of H2SO4 that's used up. So we figure out how many moles of H2SO4 will react with the potassium hydroxide. But we don't deal directly in moles, even if it were solid, and sulfuric acid isn't. Well, it's a liquid, but it's also dissolved in water. And so then we convert moles to liters and then to mils.